Let's practice using the TDS equation. So imagine that we want to calculate the change in specific entropy associated with crossing the vapor dome, and we're given that the substance is water, going from state 1, which is going to be a saturated liquid state, to state 2, which will be a saturated vapor state at the same temperature and pressure. Remember, if you go horizontally across the vapor dome, it's at fixed pressure and temperature, right? So the idea is that we start over here where the star is, move directly across to state 2. We want to know how much the specific entropy of the water changes when that happens. So we're given that the temperature is 150 degrees Celsius. That has to be true in both states, right? And the pressure corresponding to that temperature, if you look it up in the back of the book, is 4.758 bar. That has to be true also in state 2. For the other values, like the specific internal energy and specific volume, you just have to look up those values corresponding to the pressures and temperatures, either in the saturated liquid or saturated vapor state. You should have enough practice doing that by now that I'll just list these values. And remember, I'll use slightly more precise values when we do the calculation. Okay, so how does any of this relate to specific entropy? Well, it relates through one of the TDS equations. So we're going to choose T d little s equals d little u plus p d little v. A lot of students understand this equation abstractly, but then have trouble using it. All you have to do is integrate it, but you have to be a bit careful about what's being held constant and what your limits of integration are. So we're going from state 1 to state 2, just as our system is evolving from state 1 to state 2. That means that the limits of integration we choose have to go from state 1 to state 2. Let me show you. So the integral of TDS from state 1 to state 2 is the integral of du plus the integral of p dv. All of those indices are going from 1 to 2. Now you have to be careful. The variable that you put in for the limit of integration, of course, has to match the differential element, right? It would not make sense to integrate from t1 to t2 of TDS, since ds is the differential element we need to integrate from s1 to s2. All right, the nice thing is, in this particular problem that I chose, temperature and pressure are constant, so we can pull t and p out of their respective integrals like this. Hey, that's pretty nice. All of those integrals are just integrals of the differential elements. They just become the differences of the limits of integration. That I can handle. So we get T times the difference in specific entropy equals the difference in specific internal energy plus P, difference in specific volume. Okay, we can solve this for little s2 minus little s1, right? We just divide both sides by the temperature. All right, so now we have a general expression. Anytime that you have a constant pressure and temperature process, this should be the change in specific entropy. All right, great. So now we're going to make a more detailed prediction, because we can put in the values for U2, U1, V2, V1, P, and T, right? We know all of that stuff. We were either given it in the problem or we looked it up in the back of our book. So let's predict what we think S2 minus S1 should be. So our prediction is that we put all these values in. There are only two tricks to using this. One is that you put the temperature in Kelvin. Don't forget that conversion. You wouldn't want to work in Celsius or you get weird units on specific entropy. And of course the usual issue that you match the units of little u and P little v. So I looked up U in kilojoules per kilogram. Let's convert P to kilopascals. When multiplied by a difference in specific volumes, that will give us kilojoules per kilogram. Okay, so let's evaluate these, simplify a little bit. The stuff in brackets, the first term is just the difference in little u. The second term is P, difference in little v. And we'll reduce this once more until we get a value of S2 minus S1 of 5.00 kilojoules per kilogram Kelvin. Those are the units of specific entropy, remember. Okay, so we'll keep that result. That's our prediction based on the work we just did and the lookup table values in the back of the book. But the nice thing is, we can actually specifically look up the values of little s in the back of the book in exactly the same table. So for the pressure and temperature that we're given under the vapor dome, they list values of little s. So we should check that out and just make sure that S2 minus S1 is indeed 5 kilojoules per kilogram Kelvin if we use the TDS equation or if we just look it up. So according to the table, we look it up. S1 is 1.84 kilojoules per kilogram Kelvin, S2 is 6.84, same units. So now S2 minus S1, just take the difference between those two numbers, and I used a little more precision there, but it still comes out to 3 significant digits to be S2 minus S1 is 5.00 kilojoules per kilogram Kelvin. Hey, I wonder if that's how they actually calculated the value in the back of the book. They probably used the TDS equations, went through and used the other values, and were able to compute the specific entropies. Now, they had to use a baseline value. That's something that's referred to in the lecture notes, but you don't generally need to know what it is. Here, we're only dealing with specific entropy differences, and sure enough, they match up using the TDS equations or using the lookup data in the book.